Swayam Prabha. Digital India. Educated India.
Okay, so now gets to real programs. Okay. So so you have this program, okay, and initializes x equals to 0, that increments I 10 times. 10 times, yes. 10 times. And then it checks. The assert means checks that I is greater than or equal to 0. Right? Is it correct or not? What do you think? Is it correct? In a normal computer, let's say normal computer, will it be correct? At the end, it will be positive. How can it go negative? If I is a 3-bit number, maybe it will overflow at some point, right? But typically, we expect I to be a 64-bit modern computer, so there will enough space there. I have not said specifically what type of I is, but just to save notational complexity. So you have I is right. So the program is correct. So how do I make an argument? Like, what is an argument which says this program is correct? Can you verbalize the argument? You look at the code, you nodded, the program is correct. Why? You first off, see, the assert is the property. Assert is the thing that you need to check. Okay. So what's the argument? Can somebody say it out loud?
Sir, we know the value of I when the loop is completed, and for that we can assert.
How do you know it always comes back to the same value at the completion?
Sir, like we can say that the value of I is 10.
But how do you know that?
So for that we can do by saying that there is a loop in at that.
Yes, you went ahead. Yeah, loop in. I'm getting the loop invariant. Yes, yeah, you were saying.
We can put an argument that we started with an I equals to 0 and always increasing the value. So obviously it will be greater than or equal.
Yes, but to avoid the overflow, yeah, you are right. But there's an overflow issue here. So I bounded it by 10. So it cannot go above 10. So what their argument is, okay, try to listen to it. Initially it is 0, base case. Each time I make a move, I go positive. What is it called? Base case and the next one? Induction. Mathematics only have induction. We only can prove conduction. So what we prove in programs, right now I am safe, and each time I make a move, I am still safe. So therefore I am always safe. So you have to say that basically you need to find a property which initially holds, okay, which is basically a positiveness, okay, also non-negativeness, and then each time you make a move, it goes up, okay. So basically what happens is okay, so what happens is, like, you can write this program in a very nice manner: initial state, the loop, and A, okay. So this is like a graph way of looking at the program rather than dealing with a complex mess. And right, okay, let's look at a tool. It's just okay. I deleted a slide by mistake. Okay. So right. Okay. Okay. So this I am going to, these files would be in your computer also. Have you installed VirtualBox? And then you it's on home directory. Have you downloaded, installed this thing? Okay. So there is a script called run.sh. Okay. It does it gives a lot of options, and okay, it does a lot of things, but don't bother. Okay, it just does something. And since in my laptop the solc compiler are located at a different location, I will be calling a different script called myrun.sh, because it's just I have misconfiguration in my laptop. Okay, right? So see, like I try to locate this file and then run it. Okay, so that's the only difference. So you run.sh. Okay. Okay. So if so, let's look at our first program. Okay. So this is a solidity contract. Okay. So I'm written the same program which I just showed you in a solidity contract. Basically, you have this contract, and then you call this simple function, okay, and you execute this program, and then you check assert, okay, right. So you can basically say that, okay, my run.sh, okay, sorry, not run, sorry, 01, wrong file, sorry. It said something is wrong with the code. Okay, it's saying I greater than, so you can look at the output, sorry. So it says that I cannot be greater than or equal to 12. Okay, I had introduced the bug actually. Okay, so I was saying that whenever the program finishes, I is greater than or equal to 12. Right? So you cannot reach to 12. Okay? Right? So if I switch it to, let's say, 10, it says nothing. So it's like, I will show you why it is the reason it's not saying anything, but it means when it says nothing, it means program is good. Okay? So you can say it's equals to 0 also. Okay? Let's say I say less than or equal to 0. Is this a safe program? Is it a safe program? Will it be wrong or wrong? So right. So if you run it, what will happen? It is reporting an error. Okay. So right. So right. So were you able to run it? It's all C thing. Anybody managed to run it? Anybody has run anything? Anybody run it? Until you try to play with it, it's meaningless what you're looking. Okay, so always science is about doing things, not watching videos or watching lectures. Okay. Yeah.
Can you show what are the monitoring?
So you must have a folder called contracts, and it should have a file called run.sh. If you just say /run.sh and then give the file name, it should execute on that. Did you manage to run it?
Yeah.
And it shows the program is wrong?
Yes. Your transition. Warning and
Right. So you can open the file. So can you go to just open the file in, it's a Ubuntu, no? You can go to 01 simple dot.
yeah.
Right. And modify the program. Instead of 12, write 10. Yes. And then you run it again, it will say okay. Yes, it didn't say anything. So why the warning? So the compiler is giving you warning that it's a not production because we compiled it from the source code. So we didn't take the standard version. So it's giving you warning. This is not a standard version of Solidity. Okay. If anybody is trying not able to do, tell me. Stop me. You can hold us hostage until we get it done. Okay. Okay. Hello. Yeah. So quite a success rate. I see a lot of people manage to install. So this happens. Often each time you have an extra piece of technology, half the people not able to do it, and the next you take another layer, then another half of the people. Okay. So if not able to do it, it's okay. You work with someone else. Okay. And right. So and if somebody is getting very strange bugs, right? So I don't know, at least myself, I've never seen such thing before. So maybe sit with someone, please. Yeah. Okay. So okay. I showed you a glimpse of. Sorry. What chapter is this? Okay. Right. I showed you. Yeah. Correct. So I showed you the glimpse of how you can argue about a program. Okay. Now I'm going to show you what is the what this thing is doing inside. I showed you it found the bug, right? And when you gave the right assert, it didn't find the bug, right? it says program is correct. Okay. So what it is doing inside, and somebody has already said loop invariance. Okay. And I will get to that. I will try to show you the argument is inductive argument. There is a set of states which are safe states. You are there and you make a move, you remain safe. That's all. That is everything you can be said about program verification. Okay. The question is, how do you make that step? That's tricky business. Okay. Right. Okay. So what is the there was a okay. So let's bit of a history here. Okay. So Hoare is one of the great scientists of computer science, and he looked at the time of around 1950, 1960, and he said, well, people are hacking. You know, there was punch cards, a lot big computer circuits, and then just something goes in, something comes out. It looked like a mechanic shop. Okay, so you'll say this is not a way to live. Okay, like it's like chicken coop or whatever kind of analogy you're gonna give. So you say, well, no, this is not a way to live. Let's organize ourselves. Let's have a principled way of writing code and principled way to argue about it. So he was one of the first people to attempt a principle. And if I manage to successfully communicate the principle, it's fairly simple idea. It's nothing complicated about it. Okay. However, before them, it was unprincipled. So you have to understand the programming can be done in a principled manner. And today we do a lot of programming in a principled manner. Python, Java, C++ forces a lot of principles on us. We are not aware of those because we never saw an unprincipled world. Okay. Okay. So when you do import, TensorFlow, like a lot of engineering has gone to get to that point when it works that way. And import works. Okay. It's not easy thing to get it done, get it working, get it going. Sorry. Okay. So this is he said like programming should not be a hack, it should be art, and he come up with the principles. Okay. So what his principle was and how does he think about it? Let's get technical. Okay. So basically, idea is guess a superset of reachable states. Okay. And show guess is correct. Somehow you need to illustrate the guess is correct, and then you show that the guess does not intersect with the error state. Guess is basically a safe set of states. Okay. Right. So invented by Tony Ho, sometimes called axiomatic semantics, but it's basically often called Ho logic. Okay. So the Ho logic works by these triples P, C, Q. Okay. P is the set of states from which program C starts, C is the program, and the Q where it ends. Okay. So this is called Ho triple. Okay. Right. So what it is saying is, in a lot of mathematical complexity down there, but if you want to read it, but it is saying if any state you start in P, any point inside P is a set of states. You start a point, okay, and execute the program, you will guarantee to land in Q. Okay, you cannot go out of Q. You don't know where you land in Q, okay, but you will land in Q. That's the statement. And logically, I am also saying the same thing, is that if you look at if start of the program is V, you satisfy this kind of initial condition. Then you say if you execute the program P, you start from V, you land at V prime, then V prime is in Q. So this is just mathematical way of saying the same thing. Okay. Okay. So safety verification problems is slightly differently stated, in like you write asserts in the end. So which can be basically, let me show you example. Okay. So let's suppose I give you this program. I say I require something to be true at the start, so require true. Okay. Okay. This keyword will become important later because Solidity has a required keyword, and at the end I'm saying assert r equals to 2z plus 1. Okay. Is this program correct, by the way? Do you think this program correct? Z is not defined. Z is not initialized. Very good point actually, but does it matter? like,
So it will take a random value. Like
So-
the garbage values.
yeah, so is it correct with respect to any garbage value? Let's suppose they have done, okay, let me give you another assumption, which that may be they are integers, they are true integers, not integers in a programming language. They can take arbitrarily large values. Okay, then is program correct? Excuse me? I'm saying, I'm saying that it can take a, let's suppose, infinite precision computer. You have a computer, you can have as many bits you want for a number. Okay, then is that program correct? So what, is it correct or no? It's correct, right? It's correct. Are you convinced? Okay. Okay. So you start with, first focus on variable I. Okay. So I is 1. The I is less than 3 to execute one time. Then you execute one more time. By the third time, it won't execute, and then you exit. So this loop is getting executed 2 times, and then Z is being added in R 2 times. So it becomes 2Z, right? And R starts with 1, so it will be 2Z plus 1, right? So this program is correct. Okay. So in the whole world, it will be written slightly differently. It will be written like this. You start, it will be basically same thing, syntactically it looks different. So every program point is given a formula. Okay. Middle points, I don't have a formula. The specification comes at the start point and the end point. Right? My goal would be to find the formulas in the middle. It will become clear what it means. Okay? And I want to show that it starts off true and I will end with clearly R equals to Z plus 1. Okay? So this is the goal I want to achieve. Right. Okay? So there is a deduction rule systems. Okay? So basically deduction is that something you must have seen. You know, if I know few things, I can derive something. Okay? You may have seen, may not have seen, but I'm showing it first time. Okay? So there's a rule, stuff which we already know, and then we know these things, what stuff we can derive. Okay? And then you say what conditions to be met. Okay? So what, why, when you can apply this rule, when you cannot apply this rule. Okay? So let's look at few examples. Okay? A bunch of rules. Okay? Okay. So if I assign, okay, this is, so unfortunately I chose a rule which is very difficult to understand what it is doing. Okay? So, okay, so this is something which, like, if an entire lecture, this sequence, if you did not understand anything, if you can understand this thing, my life will be, like, my day will be good. Okay? So pay attention. I mean, this is if you just follow this thing. Okay? So what it is saying is, let's suppose you have a x is equal to x plus 1. Okay? Sorry. So let's suppose I have a statement which says x equals to x plus 1. Okay, let's try to understand mechanically what definition is. So let's suppose I want to say here, sorry, this is the program. And let's suppose I say I am landing here is x is greater than or equal to 0. Tell me what states I may have started. What are the possible values I started? I finished x greater than or equal to 0. X greater than or equal to minus 1. Okay? How did you get here? How did you find this? अरे algorithm लो यार, intuition नहीं. Yeah, again it's intuition, it's not algorithm. So how do I get to that algorithm? And this gives me an algorithm. And let me do the magic for you. Okay, this formula will fall out. Like, you don't have to think. Without thinking, no thinking, mechanically following algorithm. Okay, what I will do in this formula, I will put the value of this expression. You just follow. Okay. Just wherever x is, you put it there, x plus 1 greater than or equal to 0. Got it? And this works. Okay? However, it's not an easy argument why it works. Like every time I look at it, say why this works. Okay? And I have to look at the 4-line proof again and again. I have the slides, but I don't want to bore with you the exact argument. Let's look at few more examples. Okay. One dramatic example, which let's suppose again that thing, just to really understand what's going on. Okay. I'm assigning x equals to, let's say, 0, and I am landing up in x equals to 1. What are the possible states I can get there? No, I'm saying I'm landing it here. First intuitively tell me, what are the possible set of states from you get there? Is it even possible? No. Not possible, right? How did you conclude it? I am assigning x to 0 and I am saying I am always 1. How is it even possible? I can derive mathematically, algorithmically, this is impossible. How? I just simply put value of x there and equals 0 equals to 1. This is unsatisfiable formula. So actually it starts with 0 equals to 1, which actually means false. You start with false means no states. Then you start with no states, you end up there. But that means you can never go there. Okay? Got it? Okay. So if let's say put it 0 here, what will happen? It will become 0 equals to 0, it means true. So you can start with any state. Basically you're saying any state. X can be any value, it is going to get there. See, it works. Okay? So right, so basically now if I know that where do I want to go, I can figure out where to start. Okay? If it is a single assignment, for a single assignment I can do it, I have an algorithm. But the programs are more complicated than that. Okay? So what else we can do in the program? We can have a require rule. Basically, require rule semantics is that if you reach to the program point, especially in the case of solidity, you can write a require something, a require and formula, and what it means is if program reaches there and you see that require succeeds, then program continues. If it fails, so what happens is program stops. And who runs the program, you know, in the blockchain? Who is the entity who is running a program? Miner. Okay? The miner will be running the code and you will see a require fail. It will unroll all the changes has been made as if this program did not run. In the blockchain, it puts a record that there is a require failed. Okay? And anyways, whoever asks the miner to run the code will have to pay for the failure. Okay? So this, what it is saying is, what is the required semantics is, if you start with a set of states P, right, you can only land up in states where F is also true, right? So you start set of states, let's say, so if I start with, let's say, x greater than or equal to 0, and I say my require is x greater than or equal to 5, where would I land with? X is equal to 5, right? You take a conjunction of both of things have to be true, right? So, and let's suppose this says x is less than or equal to 5, then they both things are true. It will be x, when you finish, both has to be between 0 and 5. So one important, this is a very meta observation, okay? In one of the arguments I am going forward, like I start with the formula and find the formula on the finishing end, and the first one I started with the finishing formula and went with the starting one. Anybody who, like, if you do mathematics and you see this thing, you see something is off, like you should ring a bell in your head. Okay, this guy is doing something fishy. Okay, why the same pattern doesn't follow both the cases? There's a deep reason here. So this is called strongest post, the right one. The left one is called weakest pre, and there's like a lot of mathematics there. Why it is done this way or that way. Actually, both can be done in both directions. It's not like I'm just showing you the simpler way of doing it. Okay, and like it will take several hours for me to really explain things to you, but when you look at these kind of objects, you look for these strange patterns when people present an argument, okay, and see where the holes are, okay. But yeah, okay. So like for example, few examples I have shown you already. Okay, so I is equal to I plus 1. So you just put I plus 1 there, it becomes I equals to 0. We have already done that. Comes sense. We have dealt with require also, and this is one interesting example. Okay, so this is coming from actually our example. Okay, so we have okay, let's work it out. So we have assignment I equals to 1. So I should write bigger. I equals to 1, and the landing property is I less than equal to 3 and R equals to I minus 1 Z plus 1. Okay. So how do I get this formula? Put the value of I 1 there. So if put the I equals to 1, so it becomes 1 less than equal to 3, R equals to 1 minus 1, 2 plus 1. So this gets to true, so it's meaningless. So basically it has no effect, it has a meaning but has no effect. So it becomes 0, 0 times Z is 0, so R equals to 1. So it's R equals to 1. So if you start with R equals to 1, you execute 1, you get this. Okay. One important thing to note is, from here, if I give you start with this, I don't show you this, you won't realize what is written there. It's just far more complex. So just know it's not unique. Like if you go from this side, you may end up finding something strange here and something here and something there. Okay. 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 So I hope assign rule is very clear to you. Why? What did? And I could explain again. Oh yeah, sure. So this is I'm implementing the assign rule. So basically I'm saying is that if you know the formula here, where do you finish, and you want to know what formula you start with, okay, what will you do? You have a I equals to some assignment, right? Take that expression and put it here and simplify, and whatever you get is this formula, okay. And if you search in Wikipedia, it's called weakest precondition. Just search on Wikipedia, called weakest precondition. Why it is called weakest is the most number of ways, most number of states from which you can guarantee to land there. Weakest, biggest, that's what weak means, okay. In logic, big is weak, strong is small, okay, right, okay. Okay, right. Anybody confused here? Because this is very important. If you got this, rest is like one more idea I need to get across your head. Otherwise, it's.
So I got how do we go from right to left, but if we put R is equal to 1, then like we won't be able to execute.
Yeah. So it's not possible here. But there are other methods. Yeah.
So like what will the solution be for I?
So the thing is, what happens I will show you in a practical setting. You need to guess this formula. Like there is no mechanical way of finding it, and there is no algorithm of finding it. That's undecidability. Okay. You know why soft program verification? Okay, I actually never discussed this. Okay, this is amazing. Why did I miss that? So, how do you know a program is safe or not? This question. Is it a solvable problem or an unsolvable problem? It's like, can you imagine? Excuse me? It's unsolvable. Okay. How would you see it? Like suppose I give you a software which is checked by another software. What is the guarantee of this software is correct? It needs to be checked by somebody else. Okay. And then if you remember Turing machines, there's a diagonalization you can create. Okay. And a diagonalization argument will say just this no such algorithm cannot exist. So basically, who will watch the watchers? that problem which exists in our society. Like if the police start behaving erratically, okay, who will watch the police? Okay, so right, so this is the problem, and the trick we have to deploy is this. Software is huge and complex. Its verifier hopefully is a smaller program, maybe 100,000 lines. Okay, then we will build another checker which checks this software, which may be a 10,000 lines. Then we will check this software with another software which may be 100 lines of code, which human read and say this is good, therefore everything is good. Okay, and this chain is developed in a open public manner. Okay, such that everybody can, the checker, can anybody can read and say yes, it's good. And this effort is on. Like people have been building, trying to build tool chain, and this is like underlying tool chain. The software, they are called automated assisted theorem provers, and one of the leading one is called COQ, C-O-Q. It's a French word for rooster. Okay, so so you can check what COQ does, and is an Israeli system. Sorry, not Israeli. German system which is called Isabel, and then from US, you know, ACL2 something. You know that? What is called ACL2? You know what is ACL2? No. I'm missing the name. Okay, but yeah, this proof system basically they have very core simple principle inside it, and from there they derive everything you can want to prove. Okay, so this is some so in basically in a sense it's unsolvable problem. You can still have a mistake in Go and you don't know. Okay. Okay, so sequential programs are not single statements. You compose them. That is the whole point of writing a programming language. You compose things, small things, you build more complex things. Okay. So composition is a sequential composition, means one statement after another. It's very simple idea. If you have two programs written one after another, okay, if you execute from P, you land in Q, other program starts with Q, land in R, then you can say the entire program starts with P, land in R. Very simple. Okay. The important bit is this Q has to match. If there is a mismatch, you cannot really apply this rule. Okay. Okay, so let's suppose you have, I'm just building the correctness argument of the program I originally show you slowly. Okay, so right, so if I start with true and end with r equals to 1, okay, and then I have I equals to 1. Okay, so it starts with r plus 1. We know the proof of this thing, right? We presented this argument, right? And this one we have seen also, right? So now we compose them, and I know, then I execute this strand or a path of a code, it will land up in the sys set of states. Okay? Okay. Right. So this is called sequence rule. What else happens in a program? We have a sequential composition. We have is require. We have assign. What else? Excuse me. Loops. Loops is much more complex. I will get to the loop. Before loops, there is an even simpler thing which I have not handled. Excuse me. Conditions, if conditions, which is, yeah, I will get to the loop, and loop is the Achilles heel. Okay. If we don't have loops, problem is solvable actually. Okay. Okay. So if rule. Okay. So basically if rule says that basically if you start with f and p, some formula p, and you land with q, okay, and if you start with not f and p, f is the condition. Okay, f is the condition in the program. Excuse me. Yeah. Now, okay, we just do. Let me finish this this rule and flash the loop rule, and then I will finish. Okay. So if rule is fairly simple actually. F is the condition. So under the condition of true condition and a property p, you land with q. If I start with not f and p, then land it also q, then I know whenever I start with p, I will land in q. If it's true, then I still get in q. If it's false, it's also get in q. Therefore, I am always going to get in q. Very simple. This is nothing complicated about it.
So the conditions are different to land in q. So, I mean, Yeah, in both the cases, we have taken both the cases that if it's true, that's something. If one time the condition is C1 and another time condition
C2. So yeah. You need to develop the argument. I mean, this is the hard part. I'm just rule looks easy. For a human, it's much hard work. All the work is offloaded to you. You figure out what is P, what is Q, such that it works. You need to find PQs rather than they are given to you. Right? You're given a program C1 and C2 and F. You need to find P, and that's where the hard work is. Okay. Okay. So this one more rule. Okay. So consequence rule, and let me say. So let me finish this one also. So what is the consequence rule? Is saying that if I know if from P2 I can land in Q2. Okay, so it's best to drawing describes it best. Okay. So if I know that from P1 I can land in Q2, sorry, P2 I can land in Q2 for executing the program. Okay, anything smaller will guarantee to get in there. Like this entire state you can get there. Anything smaller set of states always get there, right? And here anything bigger guaranteed to be also satisfied. You start from here, you always land inside something bigger, right? So same thing is being said here. If I'm guaranteed to start with P2 and land in Q2, I can always choose something smaller P1. And if I am guaranteed to land Q2, Q2 implies Q1 means Q1 is bigger set. So you can always guarantee to land in Q1. So this is a weakening rule. Basically, you knew a lot more about the program, but you weakened it and then you turned into a much weaker argument. Why would you do this? The match sites. So many times I'm trying to match things, right? Until I cannot apply the rule. If one is not matching, you need to really apply this rule to match things. Okay. So right. So for example, if let's suppose you have these two statements. Okay. R is equal to 1, then you get to R greater than equal to 1, and R equals to 2, then you get R greater than equal to 2. You see that they are not matching. Okay. So if you want to match them, basically you weaken them. Oh man, it's a wrong example. Sorry, let's ignore this. Okay, ignore the example. So right. So this is the rule for the loop, and let's take the break now. Okay. So in this, you can see the funny thing I. Okay, and that is called loop invariant and very hard to find. Oh, let's take a break. Okay.